Hello everybody, welcome back to this training on natural language processing, and this is going to be a hands-on session. So in the previous sessions we did some formative stuff, some of the basics of NLP in terms of understanding how to represent text data in the form of a document term matrix, and we looked at the structure of the document term matrix. Each row of the document term matrix actually represent every observation, and then every column is a representation of the number of unique tokens, or the number of unique words that we have in the data. And then we also looked at some of the exploratory analysis that we typically do on text data. So the stuffs like some of the basic plots, and then context window analysis, the concept of Ngrams, and how we also looked at some of the tricks to about how we can efficiently work with Ngrams. So all that was theory. Now what we will do today is we'll try and implement all of those theory in a hands-on session using R. Now this is going to be quite short and simple, because the theory that we looked into was also pretty intuitive and pretty simple. So the hands-on is also going to be short and simple. So let's get going. Okay, so here is my R session, and to start off, let's get these things out of the way, clear up the environment as well as the console. Okay, and I don't need this, so I can close this. Okay, so this is where my data was. Okay, and I'll once again invoke the libraries. So I won't be needing dplyr for today. So I'll be invoking quantdata and read text. So these are the libraries I need, and I'll once again quickly read the data. I'm done. And let me also, in case you don't remember, let me also show you how the data looked like. So we had 1,000 observations, and each observation is actually a product review from Amazon, and then we had a sentiment flag to say whether it's a positive review or a negative review about the product. And then this thing out here, this is actually something which is created by quantdata. This is a unique key or a unique identifier for every review or for every observation. So this is how our data looks like, and what we will do is we will now look at some of the exploratory analysis. But before that, we have to create the document term matrix. I think I have to recreate it. I'll quickly do that. I'll not go through the explanation of that now, because I've already done that in the previous hands-on. So I'll quickly create the document term matrix. And yeah, so let me create the document term matrix. And I'll also, while I'm creating the document term matrix, I'm also doing the basic pre-processing in terms of converting everything to lowercase, and then I'm doing stemming. I'm removing punctuations. I'm removing all the stop words. Okay, so I'm doing this basic stuff. So which is giving me a document term matrix of 1,000 rows and 1425 columns. So these 1425, these are the number of unique words or unique tokens that I'll work with, which is so this number of unique words or number of unique tokens is also at times called the size of the vocabulary. Okay, so let's get going with the stuff that we have for today. So first things first, we will use the document term matrix to plot something that we call the word cloud, which is perhaps the most commonly seen visualization of text data, and incredibly powerful, but super easy to plot. So let me get this plotted. Yeah, and by the way, all the plots that we will achieve in today's hands-on video, they will be using some function or the other, which are part of quantdata package. So in this case, we are using a function called textplot_whatCloud, and the main argument out here in this function is the DTM, the document term matrix that we have created, right? And I can actually zoom this. So this is how the word cloud looks like. So I'll give you an explanation of this as well. So it's basically a representation of all the words that we have in the data, and the size of the words are actually proportional to their frequencies. So if you see the word phone here is having the maximum size, it means that the word phone has the maximum frequency in the data. So the term frequency for phone in the entire data is maximum, and that's why it's coming up as the biggest word in the word cloud. So that's how the size of the words are to be interpreted here. So as I was saying, it's very simple, but then very powerful as well, gives some great insights to start off with. Okay, so let me close this. So as I was saying, DTM is the main argument for the function textplot_whatCloud, because this is the document term matrix that we have created. But there are a host of other arguments as well that I'm using out here, and these arguments can be understood just by inspecting the textplot_whatCloud function a little bit. Yeah. So this is how these arguments look like. So the main argument is the DFM, or the document term matrix. Then there are things like how many words I want to plot, or what should be the minimum frequency of a word so that it should be included in the word cloud, so on and so forth. So for example, you see the min count here actually means that I will include a word in the word cloud provided it has a frequency of 3 or higher in the entire data. So then random order equal to false would mean that I really want the size of the words in the word cloud to be proportional to their frequencies. So I don't want them to be appearing in any random order. And also random color would mean that the color should be determined based on the frequency of the word. So more frequent words should have deeper color. So I don't want them to have any random color. I want the colors to be representative of the frequency. And rotation equal to 0.2. This is again an interesting thing. So it actually tells that what percentage of words I want to be rotated in the plot. So if you see, most of the words appear horizontally here, but there are some which appear vertically as well, and precisely 20% of the words appear vertically, because I have said rotation equal to 0.2. It doesn't change the insights at all. It's just for the sake of aesthetics. So instead of saying rotation equal to 0.2, I can say rotation equal to 0.5, and then if I plot this, if I just run this, nothing will change apart from the fact that we will have more words which are now vertical. So half the words will be horizontally written and half the words will be vertically written. So it just takes care of the aesthetic. So you can and aesthetic is something which is very relative, so you can do it the way you want. Okay, so that's about the word cloud. What else? You can also do a comparative word cloud. So if you recall, in the data we had 500 positive reviews and 500 negative reviews, right? So you can try to see that what are the keywords in the positive reviews vis-a-vis what are the keywords in the negative review. So one way of doing that is you can filter the data two subsets. One will be the positive review subset, another one will be the negative review subset, and then you can create one word cloud each out of these two subsets. Another elegant way of doing it is you basically you construct another document term matrix in such a way that you want the DTM object to retain the information about the sentiments as well. So typically the document term matrix will retain only the word frequencies, but here you are actually asking the document term matrix to retain some information about the sentiment levels as well, so that they can be used later on. So and the way that is done is in the DFM function, which gives the document term matrix for quant data. There's an argument called groups, and groups is basically if you have a label in your data, in this case it is the sentiment, you can basically assign it to groups and then create the DTM once again, and now you can use this DTM to do a word cloud. So we'll plot a word cloud with this DTM and see how it looks like. Yeah, so this is how it looks like. So you see there are now two halves. The lower half pertains to the positive reviews and the upper half pertains to the negative reviews. So you can clearly see that for the positive reviews, the most frequently occurring terms are great, good, these kind of things, whereas for the negative reviews, disappoint, poor, waste, money, these are the kind of words which are coming up. So it gives the entire view of positive and negative reviews together in one graph. So that's quite cool. And the other arguments are the same, so you can again play around with this argument. So you can change the rotation, change the minimum count threshold. You can do all of this, and there are a lot of arguments out here. Some of them are more frequently used, some of them are less frequently used. No point memorizing everything. So anytime you want to do a quick check of what does this arguments mean, just do this text plot underscore word cloud with a question mark. So it gives you all the documentation. So that's how I do it. Okay, so very basic stuff, word cloud, we have achieved it. Now the other thing that we looked at was something which is called a context window analysis. So just to recall what we did in context window analysis was we picked up a keyword and then we defined a neighborhood around that keyword and tried to identify that what are the words which appear in the neighborhood of that keyword. So in this case, let's say we have seen in the plots one of the most frequently appearing word is phone. So we might choose phone as the keyword and then define a neighborhood around the word phone and try and see that what are the words which occur in the neighborhood of phone. So let's try and do that, but before that there are a few tricks to be done. So I will do the tokenization once again, and I'll explain why I am doing the tokenization once again. So let me do the tokenization. Yeah, I'm done with the tokenization. Now this is something that I'm doing extra over here. So you see, I'm not excluding the stop words. I could have excluded the stop words in this step itself when I'm doing the tokenization, right? If you see the in the earlier video when I was creating the document term matrix, I was actually, yeah, so this is the part where I was creating the document term matrix. If you see, I was actually removing the stop words in the same step, but here I'm not doing that. This is the code. Yeah, So here I'm not doing that. So there are lots of ports open out here in my editor. So if you feel confused that which one I'm referring to when, don't get lost. Or don't spend too much time trying to understand that, because I'll upload all of these codes in the GitHub repository and pass on the link. So that's not going to be a problem. Yeah, so coming back to what I was saying, I'm not removing the stop words in the same step out here, and there's a purpose for which I'm not doing it. And you see, the place where I'm removing the stop words, I'm actually doing something which is called padding equals true. Okay, let me run this and show what it gives, and then I will explain what does padding mean and why am I doing it here, what's the purpose. Okay, so I have tokenized the data, right? So let me view the tokenized data. Okay, let me view the tokenized data, tok underscore data. So this is the one. Okay, yeah, so this is how it looks like. So okay, strangely enough, in the first observation, we only had stop words. That's quite crazy, but that's what it appears to be. But if you look at the let's say the third observation, there is a word great, and then there are a few blank spaces, and then there is something called job on, and then again if you look at the word review number 5, there are a few blank spaces, then there is mic, blank spaces, great. So in all the reviews you will see the stop words has been removed, the context words are present, the relevant words are present, and there are some blank spaces. Okay, now I'll come back to what these blank spaces are and why are they important. Before that, just let's try and do an experiment. So if I run this, without doing this padding stuff, which would be equivalent to removing the stop words in this step itself when I am doing the tokenization. Okay, so if I remove the stop words without doing any padding, what happens to the tokenized data? Let me check. Yeah, so here if you see, I need to run this once again. Yeah, this once again, and this is called top data. Yeah, you will see there are no blank spaces now. So review number 5 and review number 3, these had some blank spaces. You will see there are no blank spaces now. So what happens is, when you do not do padding, all the stop words that you remove, their information is completely lost. So as if as if it will appear like those stop words were never present whatsoever. So this sentence, let's say the review number 4, it looks like tight charger conversation, right? So there is, and it appears like there were, and it's very hard to tell that how many stop words were there in this sentence, because the location or the position of the stop words are also lost along with the stop words. Now on the contrary, if I do a padding equals true, then I need to run this from here. If I do a padding equals true and then I inspect the tokenized object once again, you will see that where does this blank spaces come from? So these blank spaces are the places where the stop words were located. So here, if you look at this review number 3, you easily can identify that there were some stop words in these blank spaces which has been removed, but their position information has been retained, right? And how is the position information retained? By the blank spaces. So why is it important to retain the position information of the stop words? Because what we will do here is the context window analysis. So we want to pick up a context word, and then we want to define a neighborhood around that context word, and the neighborhood can be two words to the right and two words to the left of the context word, or three words to the right and three words to the left of the context word. So what will happen, if you do not preserve the location of the stop words, the neighborhood will be very spuriously defined. Two words, like for example in review number 2, so in review number 3, if you won't have done padding, what would have happened is these blank spaces wouldn't have been there, and the words great and job one would have appeared next to each other, and as if it would appear like that they were indeed appearing next to each other in the original sentence. So when you define a context window of great, job one would actually come in the context window of great, but which may not be true. In the actual sentence, there could have been many other words, stop words in between great and job, so they may not be appearing next to each other. So because in context window analysis, it is not just the word, but their position, relative position in the sentence is also important, because you are defining a neighborhood. Hence padding becomes very important. So essentially what padding is doing is, it is removing the stop words but retaining the information about their positions, so that the neighborhood can be appropriately defined. So that's the key concept. Just wanted to emphasize on here, because if you are doing context window analysis, you have to be careful about this. Okay, so with that being done, we can now do the stemming, and let's say as we have seen that two of the most prominently occurring words here are phone and work. So let's define phone and work as our context words. You can define any word as your context word. So here I'm defining phone and work as the context word, because they are the most prominent words coming up here. For any real life business problem or real life data that you work on, the context words can be specific terms which are of importance to that particular use case or that particular project that you're working on. So that will come, that should come from domain knowledge as well, along with the initial exploratory analysis, word cloud, and this kind of stuff. So with phone and work as the context word, what I will do is I will now create the context window, and the way that is done is it's done using the quantdata function tokens_select. And what tokens_select will do is it's a function which will be applied on the tokenized data, and then it will pick up the context words. In this case it's phone and work, and it will define a window length of 5. So it will take all words, 5 words to the right of the context word and 5 words to the left of the context word, and it will define the context window in that way. And selection equal to keep means that I'm basically keeping the selection here. So tokens_select can also be used to delete some of the words. So for example, if I just quickly show you the documentation of this, tokens_select. So it can select or discard tokens from the tokenized object. So it can do a selection as well as discard or rejection. So in this case you are doing selection. So that's why we mention selection equal to keep. Okay. And once I have done this, what I will do is I have created a new tokenized object, which is basically the uh, context window of the context words phone and work, and the length of the context window is 5 words to the right and 5 words to the left of the context words. So I've defined a new tokenized object. And then with this new tokenized object, I will create a new document term matrix, which I have done, right? So let me see what is the dimension of this document term matrix that I have created. So obviously we'll have to look at the columns for that, number of columns of the document term matrix, because they represent the number of words. Yeah, so this is the one. 438. So there are 438 context words in the context window of phone and work. And what kind of context window? 5 words to the right and 5 words to the left of the context words. So the number of such words that we have got is 438. Okay, so we can now do a plot of this as well. So we can do a word cloud of this. What we can also do is we can check what these words are. Okay, so I created, so I'm basically checking the frequency of these 438 words. So I created a data frame which has 438 rows. Each row represent one of these words, and this one column which represents the frequency of this word. So just see how this looks like. Yeah, so this is the frequency of different words, okay, in the context window. You can this is a data frame, and then you can sort this data frame. You can plot histogram from this and do further analysis to find out different other aspects about the context words and the neighborhood of the context words. So there is also an alternative approach to create the context window from a quantitator. So there is a function called KWIC, keywords in context. KWIC is the acronym for keywords in context. So KWIC will also do the same thing, create the same thing that I have done using tokens underscore select. So you can get the documentation of that here. So I leave a line of code out here. I will not run that, so maybe you can try it at your end, but it does the same stuff. Okay, so we've looked at the context window analysis. So now we'll look at Ngrams. So Ngrams are a pair of words or collection of words occurring consecutively, right? So let us tokenize the Ngrams. So I have a tokenized data. I have tokenized the initial data, so broken up the data into tokens. Now I will create some Ngrams from there, and creating Ngrams would mean, you know, creating the 2 grams, 3 grams, 4 grams, so on and so forth, and that can be done using the quantitator function tokens underscore Ngrams. So I am applying the tokens underscore Ngrams function on this tokenized object, and then I am saying n equal to 1 to 1 to 3, which means I want to consider the individual words of the unigrams, the bigrams, and the trigrams, and no further. Okay, so let me run this. It is done, and let me look at create the document term matrix for this Ngrams using the DFM function. Okay, and I have created the document term matrix. So if you recall, I initially had a document term matrix DTM where I was just looking at the Unigrams. So now I'm looking at the unigrams, bigrams, and the trigrams. And when we were discussing the theory of ngrams, is mentioning that ngrams tremendously increase the column dimension of the document matrix. So it increases the number of columns tremendously. So let's now visualize, or let's look at to what extent it does that. So DTM was my original document term matrix, wherein I was considering only the unigrams. Okay, so there I had 1425 columns, or which means 1425 unique words, right? And 1000 rows, obviously. So when I have done the ngram tokenization, and that too I have just considered the bigrams and the trigrams along with the unigrams, I obviously my number of rows will not increase, that will remain the same. Let's find out to what extent the number of columns increased, and in this case I will look at the document term matrix which has the ngrams, which is DTM underscore ngram. You see, it has from 1425 it has become 3630, so that's more than twice increase by including the 2 grams and the 3 grams. So which obviously is not something that is easy to handle. So that again kind of re-emphasizes the point that we cannot look at all ngrams. We can only look at some custom ngrams or the ngrams of interest, right? So to find out which are the ngrams of interest, we can actually do a word cloud of the ngrams. Now for doing the word cloud of the ngrams, it's a good idea to not consider the unigrams, because typically unigrams will be much more in count than the bigrams and the trigrams. So if you plot all the unigrams, bigrams, trigrams together in one plot, it would be difficult to separately visualize the bigrams and trigrams. So what I will do is I'll remove one from here, which means I am now considering only bigrams and trigrams. I am not considering the unigrams anymore, and I will plot the word cloud using the bigrams and the trigrams. And let me see, yeah, so this is how it looks like. So work great, sound quality, battery life, custom service, good quality, work well, cell phone, high recommend, Bluetooth headset. These are some of the most frequently occurring bigrams in the data, and that can give you an idea about, if you want to consider some bigrams, what are the bigrams to consider. This will give you a very good idea, right? So fairly simple stuff. Now along with looking at the word cloud of bigrams, there's another way you can get some idea about which bigrams to consider, and that is again using the custom bigrams. So you can think of a scenario that you have seen work great. This is one of the most prominently occurring bigrams. So you can think of, you want to consider all bigrams where the word work is present. So it can be work underscore great or work underscore something else, right? So you want to consider all bigrams where work is present. So for that you use something which is called token and underscore compounds. So again, that's a quantitative function. When you apply it on the tokenized data, it will extract all phrases with work, and then you can select the you can do tokens underscore select to find out all those ngrams where work is present. So wherever you feel that you are not getting very comfortable with some of these functions that I am using, you can do a question mark search in the console to get a hang of the functions. They are incredibly easy, and that's one of the advantages of this Quantdata package, and that's why I'm such a huge fan of Quantdata. It comes in built with so many text handling functions that you can literally do anything by using these functions, and there's very good documentation as well. So yeah, so if you think that you need a deeper look at some of these functions that I'm using out here, you can very easily do a question mark search in the console, and you will get very good documentation about those functions and what are the arguments and how to use them. Okay, so I will now create the document term matrix using all bigrams where not just all bigrams, all ngrams where the word work was present. So that is what this highlighted line is doing. And then using that document term matrix, I'll try and see how the word cloud looks like. So this is how it looks like. So the word work is present in these kind of ngrams. So work great, work fine, work well, work good, so on and so forth. So this is so you can do this exercise with different words instead of work to find out that what are the most frequently occurring ngrams and which ones can be important for your analysis. So you can be guided by for selection of ngrams, as I was saying previously as well. It's impossible to work with all ngrams, so you'll have to apply some strategy to select the ngram. So and what are those strategies? You can first of all you can look at word cloud of all the ngrams. You can look at their frequency distributions. You can then cherry pick some of the words and see that what are the ngrams constructed with that word, and then look at their visualizations in terms of word clouds and see what are the important bigrams or trigrams to pick. And last but not the least, the problem that you will be working on, the real life problem, business problem that you will be working on, that domain knowledge will also give you more often than not, that domain knowledge will give you some insights about what kind of phrases or what kind of bigrams or trigrams to select and separately earmark them for your subsequent analysis, right? So that kind of brings us to the end of this session. So what we have looked at in this session is we have looked at how we can visualize text data using word cloud, comparative word cloud, and we have also looked at how we can do context window analysis and define context window of different lengths with keywords. We have re-emphasized on the concept of padding while doing context window analysis to define the word neighborhoods in a meaningful way. And then we have constructed ngrams, and we have seen that how just by introducing bigrams and trigrams, the column dimension of the document term matrix increases by more than 2 times. So how can, and then to keep things manageable, how can we cherry pick some of the bigrams or trigrams and keep them, ensuring that they are relevant? What kind of analysis can be done to cherry pick some of the bigrams and trigrams, and also use our domain knowledge for this purpose as well, along with the exploratory data analysis that we have done. Okay, so that's all for now. In the next hands-on video, we will look at how to construct something that is called term frequency inverse document frequency, which is a very important and very commonly used concept pertaining to representing text data. Thank you for watching. Stay tuned for the subsequent videos. Bye.